University of Michigan, will tell us about
cluster algebras and scattering amplitudes. I guess I should write this down.
I knew it was scattering amplitudes.
This is a work that has taken course over a few years with a host of people, primarily my advisor Mark Spradlin at Brown, and then associated other faculty and postdocs in math and physics. And I don't know about you, but after a hard day of physics, I like to unwind with some algebra. And that's going to be this talk after the morning's hard work and lots of good physics. We're just going to do some division, subtraction, and hopefully we'll all have just lunch. It'll be nice and simple. So.
I thought you meant like abstract algebra.
No,
just like ring theory.
No, we're really gonna just unwind with some very simple. So the idea here is in this kind of program of scattering amplitudes, which has seen some resurgence over the last decade or so, is really to sort of think about as just new ways to, I'm going to put calculate in quotation marks, but to calculate amplitudes. The idea, of course, being that the traditional Feynman prescription gives you the right answer, but it's way too much work. It's not really feasible to think about kind of solving the S matrix in a sort of way that one can understand. And so we're looking for new ways to interpret amplitudes that are more perhaps tapped into, let's say, the more fundamental ideas of the universe, and not just what we humans think of when we think of amplitudes. And in particular, as is normally the case in these kind of talks, I'll be focusing on a very nice toy example, namely n=4 supersymmetric Yang-Mills. And in particular, the kind of approach that I'm going to be taking, and I think is similar to other sort of ways that, for example, Nima and friends look at this, is I'm really trying to think about, not really try to solve the physics of n=4 Yang-Mills, but actually come at this from a mathematical perspective, and find, let's say, a mathematical question such that n=4 is the answer. So really just abandon all kind of physical motivations and really view this from a purely mathematical perspective, and see if we can kind of phrase the question in a much more natural language. And hopefully over the course of this talk, I'll kind of give you some flavor of what sort of math questions one can answer, or motivate some math questions that give us scattering amplitudes in n=4 Yang-Mills. So I'll put the outline over here so maybe it can persist. So in particular, I've got three main topics I want to cover. So a brief introduction to some amplitudes. To talk about amplitudes, we need to talk about polylogarithms, which are the actual functions that build up amplitudes. And then from the title of the talk, you can guess what this is. So I'll also want to talk about cluster algebras. And the point is that these three topics actually form a really kind of harmonious whole. And it's very surprising just how interrelated these three topics are. So I'll start with amplitudes, bridge over to polylogs, then connect back to cluster algebras, and then complete the circuit to amplitudes. So any questions before I get started? Okay, so just go ahead and start here. So start with just a general discussion of amplitudes. And again, as is usually the case, we're really going to simplify, consider the sort of most simple toy model we can. So we'll be talking about planar n equals 4, and we'll be talking about pure gluon amplitudes. So just to give you an overview of what's known, as you're probably well aware that at the tree level, this is very well understood with the BCFW recursion relations. And there are other ways to interpret tree level amplitudes in n equals 4 Yang mills, of course, but this is kind of, if you want to compute a tree level amplitude, you can plug in the BCFW recursion on your in Mathematica, and it will spit it out very quickly. Similarly, at one loop, I would say the situation is well under control with unitarity cuts. So again, this is a lot of technology developed by Zvi Byrne and Lance Dixon and David Kossower early in the last decade and in the late 90s. And again, I would say that one loop amplitudes are on the whole, well understood. So that leads us to two loop, which is kind of where I would say we've been stuck for a while. And so that will be the focus of this talk. Now I should say that when I'm talking about loop amplitudes, I'm really talking about fully integrated amplitudes. If you've heard talks by Nima, for example, he and his sort of research program is more focused on integrands and not actually getting real functions that represent amplitudes. So I want to clarify that that for my talk I'll be focused on fully integrated amplitudes. And I think a benefit of that is that some of the technology that we develop in principle can be applied to actual amplitudes that are some calculations that are perhaps relevant for LHC. Not anything in this talk, but there are some of the earlier work in this line has been used. If you've heard of the symbol, which is a mathematical technology developed in this context, the symbol has been applied for LHC amplitudes. So I'll also just say for greater than equal to 3 loops. Lance and friends have calculated the 6-particle 3-loop amplitude to like 5 loops or something, depending on how many grad students he can get typing at a computer. So there are some functions known, and then I think just recently the 4-particle amplitude or 4-particle integrand was calculated at 10 loops by Jake Bergeli and friends. And there's also a BCFW recursion relationship that in principle can calculate any integrand you want, although computationally it runs out of steam pretty quickly. So anyway, that's kind of an overview of sort of state of the art. And again, in this talk, I will hopefully kind of convince you that that the 2-loop story is also well under control.
So the unitarity cut method for one loop only works for planar, or is it?
Oh, that's a good question. No, in principle that can be also applied to non-planar. Yeah, so that's right. Yeah, so there are developments in non-planar and non-pure glue and everything, but for gluon and planar, this is sort of state of the art. So indeed, I'm going to make one more simplification and zoom in on 2-loop MHV amplitudes. So this is amplitudes with 2 minus helicity gluons and all the rest positive, which are the simplest possible amplitudes you can consider in this regime. And I'll go ahead and start by just writing down sort of what these functions look like. So I'm going to write it down, and then I'll try to explain what everything means. If I can, oh, I don't know if I'm going to be able to fit it on this board. Okay. I'll stop there. Okay. So let me go ahead and start by defining what this function refers to. So this is what is known as the BDS subtracted remainder function. So what this refers to, what this quantity is that Byrne, Dixon, and Smirnov observed that loop amplitudes in Yang-Mills had an exponentiation structure, where the two-loop amplitude could be written in some cases as a multiplication of one-loop amplitudes together. And similarly, the three-loop could be written as two-loop times one-loop and one-loop cubed. And this was looking at 4 and 5 particle examples. And so they made some guess about a general structure for loop amplitudes in n=4 Yang-Mills. And it turns out that their guess is definitely right in a case of 4 and 5 particles at 2 loops. However, starting at 6 particles, it can be shown that their guess does not capture the full dynamics of the amplitude. So the remaining function is called the BDS subtracted remainder, and that's going to be the object that we study for the rest of this talk. This function has a lot of nice properties. In particular, the BDS ansatz takes care of all of your IR singularities, and essentially all relevant color factors and everything like that is kind of bundled into the BDS ansatz. And so really, we really get just a pure polylogarithm function as the remainder. So that's what we'll be focusing on for this talk. Okay, so just for the uninitiated, this Li4 here is a polylogarithm, which is a class of functions I'll go into much more detail in a bit. And I should say that this ... here is well known, and in fact, depending on how you typeset it, can fit on a line in PRL format. So it's very compact, and it's comprised of some more Li4 terms, as well as Li3 times log and Li2 times Li2, and I'll discuss a bit more sort of what this looks like for now, but I'll just say that's known, and in principle, I'm going to be writing this kind of ellipses a lot in this talk to indicate essentially simpler parts of the function that I don't really care about, but I'll explain what I mean about that in a second. And then here in the arguments, this is, broadly speaking, the kinematical data. So this is where the actual kind of momenta of our scattering process enter in here. And that's what I would like to focus on next here. Okay. So in n=4 Yang-Mills in particular, it's actually been an interesting question to sort of talk about what do amplitudes depend on, what are the variables. Because in principle, you might just want to write them in terms of momenta, let's say, or some kind of spinor helicity formalism. But still, you have fundamentally you have to deal with the constraints that for amplitudes, you have momentum is conserved, you have massless particles, and furthermore, for n=4, you have a conformal invariance. So momenta really are not a good variable to use because they're heavily constrained, and that can really sort of muddle your functional form. So instead, Hodges introduced what are called momentum twistors. So these are labeled by the zi, and these are points in projective space that, through a fairly simple mapping, if you have a completely arbitrary collection of zi in P3, you can map that to a collection of momenta that satisfy these constraints. So I won't go into the details there, but just suffice to say that these momentum twistors can be treated as completely free variables. And so in general, we think of our kinematic space as some collection of, just call them 4 vectors. And so we can say that the kinematic space is the Grassmannian 4, n, so the space of 4 by n matrices. So this is definitely glossing over some technical points here, but really for our purposes, just think of these guys as momenta that are coming from the space of gr 4, n, and then in particular this 4 bracket that I've written here is just the determinant of the 4 by 4 minor of those 4 momentum twistors. So hopefully this gives you an idea of kind of concretely what we're going to be studying for the rest of this talk. Any questions on that? Great.
So you had the momentum conservation and the massless things, and you also said conformal. Is that an extra constraint?
Oh, just n equals 4.
No, I know the theory is conformal, but I was asking in the kinematic data. The only constraints are the ones that you wrote. Or is there some?
Right. Yeah. So in print, yeah. So we're these are constraints that the kinematical data will have to follow. Yeah. Okay. So so I can start by so over here, so you can mind what that looks like. Okay. Okay, so now I'll do a lightning review or introduction on these polylogarithm functions. So this is a very rich and old field of mathematics, and been around since 1800s. So in general, we have the polylog lik is defined iteratively in this way. And then the simplest Li1 of z is actually just a log. So polylogs are literally just kind of bundling logs together with essentially a d-log form. So Li2 is log d-log, and it's kind of scaling up like that. And then you can generalize this by, rather than essentially having just an integer index here, we call this generally the weight or the transcendentality of the function. So rather than just having integer, we can actually have a vector. So these are known as generalized or Goncharov polylogarithms. That Goncharov being the same Goncharov listed on the collaborator list, so cheat codes, that helps a lot. So this is a generalized, and there are other generalizations like harmonic polylogarithms, and etc. So, and again, in this case, G with it seeds with the logarithm. So this class right here is known as the classical polylogarithms. And then anything kind of this type, of this structure, is called non-classical. And in general, as we're studying these functions, or as mathematicians are studying these functions, it shouldn't be surprising to say that increasing weight corresponds with increasing complexity. So these functions just get more difficult to deal with as you go up in higher weight, or with more sort of entries in your vector here. And another sort of rule of the game is that we really like classical. We like classical, and we don't like non-classical. And this is just in terms of how well we understand the relationship they satisfy and their analytic behavior and all of these things. So from a mathematician's point of view, we're heavily motivated to always be working with these guys whenever possible. And fortunately, it's often quite possible. For example, at weight 1, we only have the logarithm. So any expression in terms of, you could cook up some definition in terms of non-classical polylogarithms, but you can always do some sort of identity to transform them into just a logarithm.
What is the way of avoiding the singularity in the denominator t minus a1? You have it, or you go over it or under it?
Right. No, these can be singular functions. Yeah. So.
But if it's if a1 is in that range, then do I have to choose what do I do with it?
Right. Yeah, that's a good question, and the sort of the branch cut structures and whatnot is a yeah, thorny problems. But fortunately, we won't have to worry about them for our case. But yeah, I mean, again, there is a lot of mathematics literature on studying the analytic behaviors of these kind of functions.
But they're not regular in general, you're saying?
Pardon me?
But they're not regular in general?
No, that's right. Yeah.
So are you trying to make them converge somehow? I mean, this reminds me of the Cesaro mean, or Casaro, I don't know how to pronounce that. Cesaro.
Okay.
Is that somehow you try to converge this series somehow to make them converge?
Converge in what sense? Or?
In the sense, like, if a series doesn't converge, then you define the Cesaro mean, and that you already converge better than the original series.
I see. Okay. Well, yeah. So I guess in terms of yeah, I guess
B sub k. Well, I mean, maybe you'll tell us later.
Yeah,
how this works.
Yeah. Hopefully, I can keep introducing them, and if you still have a question, bring it up again. So this is also true for weight 2. You could, in principle, cook up some non-classical, have some interesting vector here of weights, but it's a theorem that any way that you do this, you can rewrite it as actually a collection of Lie-2 and log squared terms. So essentially what this is saying is that in the space of polylogarithm type functions of weight 2, that space is spanned by the classical polylogarithms. And I should also mention that we also technically have terms proportional to pi squared. Pi has transcendentality 1, and so we can have constant terms as well, but I won't really worry too much about them. And this actually, this continues. So in weight 3...
By pi, you mean the number pi?
The number pi, yeah. So for example, I mean, there are identities, which I'll get into in a little bit later, where you have a sum of Li2 terms, dialog terms, and that sum simplifies to a collection of log squared terms plus pi log plus pi squared with some. So that's the kind of game that they like to play. And so similarly with weight 3, and again, I'm trying to emphasize these generalized polylogarithms form a vast space. So there's a huge number of ways that you can define these types of iterative logarithmic type functions. And mathematicians look at this and say, but it turns out that for low weights, any complicated non-classical function that you write down is secretly equivalent to a much more simple collection of classical polylogarithms.
So in weight 2, you could have also had pi log.
That's
in
right. Yeah,
addition to-
yeah, you can have pi log. Yeah.
Pardon me, how's the weight defined for non-classical?
Yeah. So for the weight, you just add up. You know, it's
no.
the length. I think
Oh,
of
okay.
this guy. Yeah. So you can have Li2 log, etc. So far we're really happy. In particular because it is a statement that, for example, Li2 only satisfies one functional identity. So there's only one functional identity among style algorithms, and any other expression that you might write down that simplifies is because of that one functional identity. So it's very well understood kind of what these functions look like. Li3 is a little more complicated, but still it's well understood. So things get more complicated when we start talking about weight 4. And in fact, so weight 4, again, you could have Li4, you can have a Li2 times a Li2, you can have Li3 times the log, etc. You can have pi times Li3. But it's, again, a statement of mathematics that there exist polylogarithmic type functions that are not expressible with this basis. And so you need to have, there exists some non-classical polylogarithms, intrinsically non-classical. Fortunately, at weight 4, you only need to add one non-classical polylog to your basis to span the space of weight 4 polylogs. And so I'm just going to write down a function that's going to be my choice. And this is very pointedly an arbitrary choice. And so I'm going to define this guy, V2 yeah. So this is a non-classical polylogarithm, and it has the structure again. It's like you're kind of gluing together polylogs with oh, I guess this would be over T, since you need a D-log form. So again, you're kind of gluing together polylogs via integration this way. So it is a statement then that these functions, along with this function, correspond to a complete basis for polylogarithm functions of weight 4. So fortunately, I can stop telling you this kind of boring story now, because so this function that we care about, this remainder function, for MHV amplitudes at least, is understood to be of weight 2L. So the L loop remainder function is of uniform weight 2L. So you have everything, essentially all the weights always add up to 4. So you never have to worry about just having a log at the end. Everything always adds up to 4. You could have a pi to the 4 at the end, but uniformly of weight 2L. So if we're considering 2-loop amplitudes, then I can just say that this is going to be some sum over Li22 plus Li4 plus da, da, da. So this is the kind of function that we're going to be analyzing.
So
Oh, yeah.
is there just an independent definition of what the transcendentality of a function means?
Right. Yeah. That is a good question. Indeed, I think it's the weight. I mean, I think the best I could say is it's the idea of weight as defined in pi logarithm, and then pi, and then like Zeta functions are of transcendentality 1. But yeah, that's a good question, and I haven't read enough in the math literature to know a more kind of better definition for transcendentality.
So,
Yeah.
so how do you show that the reminder is weight 2L? Is it?
Yeah, that's right. So that's
It seems to me,
go ahead.
yeah, that you have to kind of, you have to know how it behaves for like very high load, so you can prove it for.
Yeah. So that's right. This may very well be a conjecture based on the 10 loop, example. So essentially, once you start looking at the integrand, you can look at basically the pole structure in the integrand, and I mean, essentially, if you think about it in a simple way, it's like you get 2 propagators per loop, and so that gives you some that corresponds to these d logs essentially. So yeah. Okay, so this is just to give you an idea of what this function that we're looking for, and again, if we're taking this from a purely mathematical perspective, now I just want to start asking questions about the space of these functions. So at this point, I'm going to take unfortunately another. So I would say that perhaps amplitudes and polylogarithms have been introduced now. So I'm going to start by moving on to cluster algebras, which is the other main ingredient here. So cluster algebras are it's a relatively new area of mathematics. They were first introduced by Fomin and Zelevinsky.
But actually, before you go on,
Yeah.
just to make the connection, you said that there are some polylogarithms of some weight,
Mhm.
but as functions of what? In other words, I know of your kinematic invariance, but
Mhm.
is there only one?
Right. So, I mean, well, in principle, these arguments could be arbitrarily complicated algebraic functions of these 4 brackets.
Mhm.
So that a priori, it can be anything, and you have 6 in the 6 particle case. You have 6 choose 4 brackets, and due to a special feature of n equals 4 Yang-Mills, they do have to appear in these cross ratios, but any arbitrary function of these cross ratios could be an argument of the polylogs. Does that answer your question?
The planar nature play a role?
Right. No, exactly. Yeah. So that's for the cyclic symmetry. Indeed. Yeah. That's where the planar gives you the simplicity. Yeah.
So there. Okay, I still didn't quite understand. So there's only one way it can depend on these variables. I mean, it's some weight 4 function.
Yeah.
But on the kinematic data, it's then given by this sum over cyclic permutations of these cross ratios.
Sure, but again, what appears inside these parentheses
Mhm.
could be arbitrarily complicated. It could be square root of this. It could be
I see.
the square root of this plus pi,
Uh-huh.
pi root of another thing. It could, well, maybe not pi root, but it could be.
Okay.
And indeed, when this function was first calculated, it was 17 pages long, and the arguments were essentially complicated algebraic functions with these ratios. So it's a huge space of you can't just write there. It isn't. We're not done yet. Okay, so cluster algebras are. I'll just try to write down. Loose definition here. So there are variables, some variables which we call cluster coordinates, and they are grouped together disjoint sets, which we call clusters. And these clusters satisfy relations via a process called mutation. So I think probably this is quite vague and leaves people mystified. So let me give you some example physical applications. We are fortunate also to have in the audience Danji, who has done a lot of work on connecting cluster algebras to physics. So one example would be essentially Seiberg dualities on quiver gauge theories. Another example are BPS quivers and wall crossing. So this is Dan as well as Gayoto and Moore and Andy Knightsky, who was actually the first person to teach us about cluster algebras. So they also appear in Y systems, which is interesting. And actually, they also appear in another area of amplitudes, namely the integrands. And there is a story, again, by Nima and friends for doing the integrands in terms of this structure on the positive Grassmannian, and they see cluster algebraic structure at that level as well. I won't talk if it's, I don't know if it's connected to our story, but there are other examples in the physics literature. So because again, this is still very abstract, let me give you a straightforward example, the simplest possible example. So the simplest example is actually where you start with the Dinkin diagram A2. So again, this is essentially, so you have some quiver. I'm going to label it in this way. And the idea is you start with what we call a seed quiver, and you pick some node on the quiver to mutate on. And when you mutate on that node, you get a new quiver. And then the variables here are the cluster coordinates, and the grouping is a cluster. So let me write down the rules for mutation. So when you mutate, you get to you redraw all of your variables. In particular, if you're mutating on the kth node, you get where BIK equal to the number of arrows. Okay, so again, maybe this seems a little abstract, so let's just go ahead and calculate the cluster algebra for A2. So I'm going to start by choosing this node to mutate on. And so I will get a new diagram, a new quiver. So this guy just flips. So the node you mutate on just flips. The arrow flips as well. I didn't write the rule for rewriting arrows, but it's relatively straightforward. So the arrow flips direction, and you get a new cluster coordinate here, which is going to be, in this case, the original one times 1 plus the mutated node. And so in this case, we get the original one, so 1 over x1, and then it's just times 1 plus x2. Because in this case, BIK is just 1. So that's exciting. And if you play this game again and mutate on node 2, you go back to where you started. So we can continue. So let's mutate then on this node. maybe I'm gonna move this up just so people can see. Okay, so we started with 1 over x1 goes to x2, and we mutate
So
to,
look,
yeah.
the A2 quiver
Mhm.
is just 2 nodes and an arrow.
Yeah.
But what's the significance in deciding to label one 1 over x1 and the other one x2?
You'll see in just a second. It's just a convenient choice. Yeah, in principle, this could just be, these can be arbitrary. You can label these arbitrarily. Okay, so if we mutate on this node now, so now I'm going to keep drawing these clusters, and this kind of line just shows that they are connected via mutation. So if we mutate now on this node, so again, that one just flips. And the new one that we get is, I won't go through the algebra, but you get this. Okay. So now, so we mutated here, then here, now we mutate here. So again, it flips. And make the arrow going to, and again, each time I'm writing new variables here, it's just following this rule and just saving you some steps. Okay, now you can maybe see where I'm going here. So if you mutate here, get x2 over 1 plus x1 goes to x1. And now if we mutate here, I get back to where I started. So this is the simplest example of a cluster algebra. You can see that it's closed up. Essentially, we often talk about this as a pentagon, because we have these 5 connected in this way. And so again, the clusters are essentially the nodes of this pentagon, and the cluster coordinates are just the actual things that live on the nodes of the quiver. So again, this seems like kind of an arbitrary set of rules, but Fomin and Zelevinsky showed that that these rules actually sort of provide machinery for explaining a lot of things. Again, for example, rewriting the content of quiver gauge theories as you do Seibert dualities essentially follows these mutation rules. But I'm not the expert on that. Dan is, so if you have questions, ask him. And there are a wide range of interesting applications for these kind of rules in mathematics. So why am I bringing this up? So in the context of polylogarithms, actually this.
What's again the definition of cluster algebra?
So the cluster algebra essentially is all of the relationships that are satisfied by these collections of variables with these kind of quivers and this active mutation connecting them. So yeah, I mean.
What do you mean by relationship?
So the relationship being that if you mutate, so this collection of variables is related to this collection of variables by mutation.
By this map.
By this map, exactly, yeah.
Which reverses all the arrows, and I could apply this to an arbitrary
quiver, yeah.
graph, nodes and arrows.
Yes.
With a different variable assigned
Yes.
to each one.
Actually, one of the mathematicians, Keller, who's worked on this, has a Java applet you can download, and you can draw an arbitrary quiver, and you can just click nodes to mutate them, and he'll redraw all of the variables, and it has cool music, and it's very fun. It's for your video game for your kids, yeah. So.
And
you will always go
general
back to
node will. Oh.
Yeah, so you won't in general close on yourself.
Oh,
Yeah, so you can have infinite cluster algebras.
you can.
Yeah. And we might encounter one if we're unlucky. Yeah. So again, yeah, you can write down an arbitrary quiver, and your quiver can actually have you can have more complicated arrows. You can have there are extensions where you can add weight to your arrows and all of these things. And in fact, some of these physics applications have motivated extensions of cluster algebras. So this particular A2 is actually quite useful for us because of the following identity. So there are 5 distinct coordinates here, modulo inversion. So there's x1, x2, there's this guy, there's that guy, and there's this guy. So if these are x1 through x5, then as arguments of V2, they give you 0. And again, this is 0 plus terms that are like log squared. But for my purposes, those are the interesting statement is that you started with what appears to be an intrinsically weight 2 thing, and it's actually just a product of lower weight functions. So the mathematicians often work modulo products of lower weights because they're sort of simpler to deal with. But you can look up on Wikipedia what the actual full thing is, and this is actually due to Abel in, I think, 1882 or something like that. So this is well known.
So I missed it. So the xi's appearing in that sum are the ones that the arrows point to in each cluster?
Oh no, it's just the distinct. You look at all of the clusters, look at all of the variables, there are all of the coordinates, and then modulo inversion. So you don't think of x1 and 1 over x1 as distinct.
Which one you pick?
I mean, I guess for this one you would pick the ones that I had circled, and you would pick. I mean, in principle, it doesn't matter. You can rewrite this identity depending. I mean, okay, let me back up.
So you're saying Li2 of x and Li2 of 1 over x are related
They're-
up to terms of
yes,
the
exactly.
log squared?
Yes. Yeah. So, indeed. So.
And you haven't. Is it now obvious why, or should it be obvious why you choose 1 over x1 to begin with?
Oh, that's that way just so that when I mutate on this node to get back, if I start with x1 goes to x2, and I do this chain, I actually get back to like 1 over x1 goes to 1 over x2 or something. I forget. This is a slight sleight of hand. Maybe it was not worth everything, but. Yeah, I think actually technically to get back to where you started, you have to do 2 loops, like 2 circuits to deal with all the inversions. But again, I don't really care about inversions, so so yeah, maybe it would have just been easier to start with x1 goes to x2. But yeah, so again, the idea is that you play this game, you see what kind of collections of variables appear, and then it turns out that there is this very, I think this is quite striking. So this is, and I said this is the one and only functional relationship that the dialog satisfies. So, in some sense, cluster algebras are giving you some firepower in the realm of polylogarithms, and this kind of motivates us.
Is it generalized to sum of an?
No, exactly. So that's the question. So the question would be. Is there some general way to say that, can you say a sum over cluster coordinates gives you something? I'm just going to call it interesting, not even 0. I mean, this is this is a quite striking example, but I would be satisfied for, is there a general connection between cluster coordinates and some nice polylogarithm type function? And so this is a question that our collaborator Sasha Goncharov had been studying a lot before we came along. looking for cluster coordinates, so for example, it is not the case that Li3 applied over the variables of A3 gives you 0. But you can, but that would be kind of pie in the sky, right? So this is, so more generally, you want to look at polylogarithms of various weights applied over various cluster algebras of Dinkin diagrams or other diagrams, and then see if you get something to work out. So this is the kind of question that that Sasha was looking at, and he came along, or then basically we were as physicists looking at these functions, and we saw originally these functions were written in terms of the Goncharov polylogarithms, and so he happened to be at Brown at the time where we were, and so we just went to his office and asked him, so can you help us with these crazy polylogarithm functions? And he looked at the functions that we were looking at, and a big light bulb went off, because it turns out that there exists a cluster algebra on GR or general K, N. So there's a way of writing down a quiver. Given a Grassmannian, you can write down a quiver, and that quiver generates a cluster algebra. And in exactly these ratios that appear are the cluster coordinates that you get from that. So this is kind of actually the main takeaway here of the talk, is that in fact we find that if you sum over GR4, n cluster coordinates, you get an amplitude. So this is obviously a gross oversimplification of what actually happens, but this is, again, the takeaway is that the kinematic space that we are thinking about has a cluster algebra, and cluster algebras have an intimate connection with polylogarithms, and that connection lets us write down amplitudes in a very essentially algebraic way.
And the polylogarithm is what's the weight of
so it will be generically, so it'll be Li4, but then there will also be this non-classical one that I mentioned, in addition to log squared and Li2 log squared and all of these things. But that's kind of the rub. That's where I'll focus on exactly which polylogarithms and exactly which cluster coordinates. Is what I will try to cover in the next some time that I have. So, any other questions?
I have a naive question.
Yeah.
For this one, in order for it to encode the amplitude information in the physics, I just don't see which part is that information encoded.
So the information comes from essentially what we choose to put as the label of our vertices will be functions of momenta.
Okay, and in this case, is the Grassmannian foreign you introduced earlier?
Yes.
But does that distinguish which process? I mean, a specific process, or?
Yeah, so you can basically, it gives you a generic function, then you plug in your momenta, and it'll spit out a number, which is your amplitude.
Okay.
But so I can start by going ahead and writing down.
So you're saying when you plug in specific momentum, it's one of these cross ratios, and you said there can be many of these cross ratios.
No, so I mean, this one here you can think of as a label for the momenta of particle one.
Yeah.
So we've labeled, so you plug in its 4 momenta through the machinery of momentum twisters, and this evaluates
I'm just trying to
a number.
You have your set of cluster coordinates, which you've labeled x1 through whatever.
Yeah.
And I want to know what you replace x1, x2,
So
and so forth.
I'll write that down. Yeah. So I will give you now. I'll show you what this cluster algebra, what this quiver looks like for this amplitude. So this is so again we're going to be talking about R26, which is equivalent to the Grassmannian 4,6, which and again I won't be able to explain why this is, but you read just one of the first introductory math papers on cluster algebras, and it turns out that the cluster algebra on GR46 is actually equivalent to A3. So that's nice for consistency. So I will show you now.
Sorry, when you say cluster algebra on something,
Yes.
what do you mean?
So essentially, yeah, that's a good question, and it kind of, to fully answer that, I have to go into a lot of technical details, but essentially.
Don't you just have to tell us how to build a quiver?
Yeah, no, that's
given
right.
KNN?
So I'm going to write a quiver where the nodes are dependent on GR4,6 variables, and why this one is particularly, in principle I could write down whatever I wanted.
Right. That's.
Yeah. So why this quiver is precisely rated GR4,6 is yeah, it's a more technical.
You seem to be saying something different, right? I mean, you don't say like take a quiver and then put.
Yeah, you can't just
You
put
said, like,
you can't just put
just-
anything in on the nodes. You have to put specific things, and those specific things are actually motivated by so the kinematic space is actually, so it's really these momentum twisters live in P3, and we can think of the formal mathematical name for this kinematic space is not GR4, n, but it's the configuration of n points in P3. The n points are essentially our particles, and then you have to modulo out by this conformal symmetry, and there's also a dual conformal symmetry in this context. And when you do that, you actually end up with a Poisson structure on your space, and that Poisson structure tells you how to write down these quivers, which is, again, a lot of words, and I don't have time to go into it. But again, it's a rigorous, well-defined process. But for now, I just have to kind of write down what these quivers look like. So here is a seed quiver for GR4,6. And again, I'll say the way that you arrive at something like this is that, again, there is actually this this Poisson bracket that you can define on this space, and ratios that have Poisson bracket 1 are you can actually calculate this, and you get Poisson bracket equals 1. They're connected by an arrow, and so you can just write down a list of these cross ratios and determine what the arrows look like by calculating the Poisson bracket. Okay, so here's our seed quiver, and we can go ahead and start playing this game of mutating on different nodes. And it's actually pretty easy to start with because we can just, for example, for a second, just hide this guy and forget about it, and now we have an A2 subalgebra. And so we can play the mutation game and generate essentially a pentagon like I did last time. And then you can, let's say, forget about this guy and play the game here, and you get also a pentagon. And if you play the game, it actually closes up to form a nice polytope, which I'll maybe draw over here. And we'll also stress my artistic abilities. But the polytope looks like that. Okay, so here we have what's called the generalized the Sheff polytope for A3. It has 6 pentagons. I should say, again, to reiterate, at each vertex in this polytope lives a quiver that looks like this. Maybe the arrows are slightly redrawn. But at each vertex, there is a quiver. And then the lines signify that they are related via mutation. And each vertex has valence 3 because there are 3 nodes that you can mutate on. So there are 6 pentagons, which are related to the 6 A2 subalgebras. And then there are 3 squares. Here, here, here. And these are essentially A1 cross A1 cluster algebras. So for example, if you have like X, Y, and then some other ones, so you need, and if X and Y are not connected by, let's say, so if X and Y are not immediately connected by an arrow, you can go to the 1 over X, Y, and then you can go to 1 over X, 1 over Y, and etc. So that way you get 4 distinct clusters that are related between these two A1 cross A1s. So this is A2. And then there are, it turns out that there are 15 distinct coordinates that appear. And there are 14 clusters or vertices. So as you can see, actually, this ratio right here is precisely this ratio that appears in the amplitude. And this is really, I think, a fairly striking fact. I mean, it's really striking if you keep in mind that this argument could have, in principle, been an arbitrarily complicated function. So the fact that simple cross ratio is impressive. And then furthermore, okay, this probably won't totally blow you away, but with 6 particles and these 6 choose 4 brackets, you can write down 45 distinct cross ratios. So only 15 of them are actually what we would call cluster coordinates. So that it could just be coincidence. It could just be that the amplitude only depends on these coordinates, and these coordinates just happen to be cluster coordinates, but they could have been some of the other cross ratios. But still, I think it's important to note that an arbitrary cross ratio does not have to be a cluster coordinate. Cluster algebra picks out a privileged set of cross ratios.
So is this an observation, or is this derived?
What exactly? Which? So this.
I'm just curious. Sorry, I wasn't following that. So do you get this? Is this conjectured relationship between the cluster algebra and then you know the form via?
Oh, that's right. Yeah. So this is an observation. Like this was calculated before we knew what cluster algebras were.
Right.
And then we just looked at what appeared in the arguments. And actually, in fact, there are only 9 distinct cross ratios that appear. All of those 9 happen to be cluster coordinates. But that didn't. It did, in no way, shape, or form had to be that way. Okay. So and so indeed, this whole expression, including even the lower weight terms, the Lie 3 times log and all of that, are just cluster coordinates. Okay, so maybe this is still just seems kind of, it definitely could have happened by chance. So let's do a harder example. So let's do the 7-particle 2-loop amplitude. And it turns out this is equivalent to the cluster algebra on E6. So I'm not going to draw a quiver, but they exist, and I'm not going to draw the polytope because it has 1,071 pentagons, 1785 squares, 385 ratios appear, and there are 833 clusters. So actually, there was an undergraduate working with us at this point, and he actually made a pretty graphic of this in Mathematica, and it's cool. If I just had a slide, I would show it. But anyway, so you can go ahead and again play this game, and you can try to calculate the amplitude, and you can see, does the amplitude depend on these coordinates? And so we did that, and it was very difficult to calculate this, but we found, and by calculate I mean we guessed a lot of things, and we made ansatz and imposed correct physical behavior, like smooth behavior under the collinear limit and all of these things. We weren't trying through Feynman diagrams to do this. So we actually did find an expression, and it involved this new function that I described, and then it had some over Lie 4s, and etc. And at first we were really excited because the expression that we found, these variables x and y that appeared, they always appeared together on square faces of this polytope. Let me redraw it, I guess, actually. So again, what I mean by that is, well, whenever we had an x and a y pair, you could always find a square face where every single vertex had a cluster with x and y in it, which is a really non-trivial statement. So there's a real very explicit map between squares of this, and again, I have to remind you that at each vertex of this square lives a cluster that has certain coordinates. So there are variables that live on each vertex, and each square has a collection of variables associated with it, and there would always be an association with these terms. So it seems like the structure of this polytope was informing the functional form of the amplitude. The problem was that in order to make this work, and again by imposing like correct collinear limits and correct physical behavior, these had to be garbage. By which I mean very complicated algebraic functions, not simple ratios, and not even cluster coordinates, like or functions of cluster coordinates, but not explicitly cluster coordinates. So this was a real bummer. However, in talking to our mathematician friends, it became clear that, well, what if you just chose a different non-classical coordinate, or non-classical polylogarithm? Is there some way to redefine your function, or choose a new function? Again, we only had to choose one non-classical. We could have chosen a different one that maybe, due to some relationships with Li4, cleaned up the garbage or something like that. And it turns out that, indeed, it's actually a very sort of, I would say, important question to ask in terms of really, so it seems kind of arbitrary to ask, what do polylogarithms like depend on? So again, I chose this Li22 as my one non-classical, but I could have chosen a different one. And you can even redefine your functions by changing the limits of integration so that the actual arguments change. So really, the argument of a function seems kind of like an arbitrary thing to focus on. And indeed, it turns out that that this had upset mathematicians for a long time, and they were able to expose some additional structure in polylogarithms that clarified this. And it actually turns out that polylogarithm, the actual functional form, is not really what you want to work with. And this is particularly true because the space of polylogs forms a Hopf algebra, which I don't have time to go into, but there's a lot of structure in this kind of graded space of polylogarithm functions of weight k. And in particular, there it also has a Lie coalgebra, which I'll denote by delta. And this is what I want to kind of hone in on. So this is an operator, this coproduct delta. And what this delta does is it unbundles polylogarithms. So again, you can think of polylogarithms as being logs glued together into successive integrations. And this delta undoes that and breaks it up into its constituent parts that you can study more clearly. So this is, again, very abstract, and I don't have time to go into the full mathematics of it, but there exists a map, which I'll use curly L to denote the space of polylogarithms of a given weight. And it takes you to essentially breaking up a polylogarithm into its constituent parts that you would, in principle, then integrate back together. And I have to emphasize that this map is just there's simple algebraic rules for, given a polylogarithm, calculating delta of that polylogarithm.
Sorry, can you say a little bit more about what you mean by the product?
Yeah, so I'll just give a simple example in terms of what this delta looks like.
So like the coproduct of the whole function?
So this is actually distinct from the coproduct. Yeah, the coproduct of the Hopf algebra is capital delta, and this is the coproduct associated with the Lie coalgebra, which is a different additional structure for that polylog satisfy.
So you have two coproducts?
You have two coproducts, yeah. But this is, and they're kind of complementary in terms of these understanding of the structure of these functions. But let me just give you a quick example. So delta of, I should say, so in general, if you start at weight 4, you can imagine this as having two components. You can glue together two Lie 2s, or you can glue together a Lie 3 and a log. That's two ways to get something of weight 4. So, in particular, the L3 wedge L1 component of Li4 is essentially just Lie 3 and again, all this is saying, I mean, if you remember the definition of Li4 is literally just Lie 3 d log. So that's, again, you can have this idea of it unbundling the integration. And interestingly, the two wedge 2 component is 0. So you're not trying to mash together two like a Lie 2 times a log d log. You just have Lie 3 d log. So that's one example of what this is talking about. And what's interesting about this map is that, as I said, for weight 3 and lower, you only have classical polylogarithms. Classical polylogs span your space. So whenever you project down to these spaces, you only ever have to deal with classical polylogarithms, and all of these issues of having a vast space of complicated non-classical polylogarithms disappears. So let me give you an example of what.
So
yeah.
Just for Lie 2, 2, it would just be Lie 2 wedge Lie 2?
Yeah, so I'll show you exactly that. So let me show you an example of what it looks like for Lie 2, 2. Yeah.
And this wedge
Yeah.
is just a formal symbol at this
Yes.
point? Okay.
Yes. Goncharov was very insistent that it be this particular symbol for reasons that he understood very well, but I don't know that we did. Indeed. So let's look at this example of a non-classical polylogarithm. And indeed, as you correctly guessed, we can really think of Lie 2, 2 as mashing together two E2s. Which is very nice. However, this is where the real problem comes in, which is that if you look at, ideally, you would love for this component to be 0 because it didn't seem like we had anything to do with Li3. But you can actually go ahead and calculate it, and it looks pretty bad. So I'll just write down one term. So you can write it in a way that's 12 terms long, and you get these messy arguments where you have some rational function of x and y like that, and this is, and it's quite long, and there's quite a lot of messy stuff. So this is sort of problematic. But now what's amazing, and maybe you saw this coming now. So we tried. So okay, but I should say again why this is an important thing to do is, again, this delta moves us to a space where it doesn't matter how we defined our non-classical Plio logarithm. So this arbitrary choice, any choice that we made would still map to the same expression in these two spaces. And it's in fact it's a unique map. So given an element in and B, in L3. So you need both. You need an element A and B in these two spaces, but that's in direct correspondence with some function in L4. Okay, so this amplitude has a unique A and B, and no matter what choice we used for defining this function, we'd still get to the same A and B. So it essentially tells us what the true function is. So we calculated delta on this guy. So again, it has an L2 wedge L2 and an L3 wedge L1. So again, just by looking at that map, we can immediately know what the L2 content is. But then when we look at the L3 wedge L1, first of all, we have to do L3 wedge L1 of the garbage, so we get some of these type of terms. But then we also, these guys, the L2, LD222s, also had garbage. So you can probably guess what miracle occurred, is that all the garbage cancel each other out, and you ended up with L3 x log y, where again x and y are now cluster coordinates on this space. And the real magic, the real pièce de résistance is that these x and y were not arbitrary x and y, but they always appeared together as generators of an A2 algebra. So this is completely crazy. If you look at the Mathematica file for these things before you combine them, it's like megabytes of gross algebra, and it simplifies to be pentagons. And then the really crazy thing is that for every three, you can find 3 squares in this sum that combine with 6 pentagons in this sum to form an A3 algebra, to form this guy. So again, remember, this polytope for GR47 is ginormous, but you can always, I really should not have erased this so many times, but you can always think of this as a sum over A3s for some function, say x1 So this polytope is ginormous, it's disgusting, but it has a plethora of A3 subalgebras, and you can pick out a select few A3 subalgebras, and they essentially have functions associated with them that give you the amplitude. So this is like totally crazy from our perspective. And I'll try to kind of emphasize a little bit in the last 10 minutes or so that I have kind of really how profound this statement is. But again, just to recap before I continue, what we found is that there's a way to understand this amplitude as a sum over these polylogarithm terms that essentially encode the structure of this polyhedra for this cluster algebra.
So if you want to actually compute the amplitude,
Mm-hmm.
which do you have to sum over all the
Right.
A3s, or like
So
which one you have to choose?
yeah,
and
exactly. That's still something we're trying to figure out. My dream is that
That has to be also there.
there's like
But
some beautiful subalgebra
But
that
can I
you
say-
sum over entirely.
it seemed to me that even in the lower case,
Mm-hmm.
that wasn't clear, right? Because you said that the lower, whatever, Li4 depended on 9 coordinates, but
Yeah.
you had 15 coordinates.
Yeah, that's right.
So
Yeah,
even
yeah,
then,
exactly.
there is like
Exactly.
an arbitrariness.
So a surprising thing is that the number of distinct coordinates is 9/15 of the total number of coordinates. Is 9/15
Oh, I
times
see.
385. So that's a surprising. That we don't know if there's like always some privileged 9/15 of cluster coordinates or something like that.
9/15 of the old
Of
A3s
385, yeah, yeah. So again, basically, given what we now have is if you give me an A3, and again, in principle, this can be any A3 you want, x1, x2, x3. I now have a function, a polylogarithm function of weight 4 that I have identified to this A3, and in some sense, it encodes the structure of the A3 because the L2 wedge L2 component is just the squares, and the L3 wedge L log terms are the pentagons. And in the last minutes, again, I'll just ask the question, kind of what is this function, and how, like where, we arrived at it kind of through luck and through brute force, but had we been smart, how could we have found this function? So how unique is this function?
Is it the question that will end you on Hannibal Fork? No.
Well, so actually what's cool is that, let me start with a very generic question. I just have a generic A3 cluster algebra. I'm a mathematician, I know nothing about n equals 4. I just have this algebra, and I want to construct a function, call it a little f, and I say I want this function to, again, encode this cluster algebra in some way. So I'm gonna ask, how can I put some coefficients like this, and then coefficients again for the Li3 log terms, and I want to just construct the most generic function. Now this again is going to be something that's annoying to just pull out of the hat at the very end, but the additional structure, one of the key features of the Lie coalgebra of this coproduct delta is that you need delta. Well, is that basically delta squared equals 0. This is a generic feature of the Lie coalgebra, and so this is essentially you can't just put arbitrary coefficients here and expect it to be connected to a real function in L4. So we construct this ansatz and we say delta of f, and we set this equal to 0, and there is a unique answer. And that is precisely what we reverse engineered by laboriously doing the 2-loop 7-particle amplitude. So there essentially is only one way to connect cluster algebras and polylogarithms of weight 4. There is just a unique map between an A3 algebra and a polylogarithm of weight 4. And that's, again, a purely mathematical statement. Goncharov was super surprised by this. But if you just say, again, give me a weight 4 polylogarithm that depends on this cluster algebra in a well-defined way, there is no choice. You have one.
And the number of particles, where do they?
Oh, so this is, I mean, again, this is just pure. This is purely math. There exists. So now,
I mean, is this a statement for that cluster algebra?
no, this is, I mean, this is for any A3. So this
Oh,
is just for
A-
A3.
Oh, A3.
Yeah, sorry. So this is a sum over.
Oh, I see.
Yeah, sorry. Yeah, that's right. So this is just a generic A3. There is only one way to connect that with. So essentially, if we want to view so another way of saying this is, based on the 6-particle example, we conjecture that the n-particle amplitude will depend on cluster coordinates. It's a weight 4 polylogarithm that depends on cluster coordinates. That is our conjecture based on this simple example. What is the space of functions that depend on a cluster algebra? And there is just one function that depends on it in this way that satisfies the Lie coalgebra and stuff like that. So again, this is sort of at the end where I'm getting in the more technical part, but the point is that by asking very natural questions in mathematics about kind of how to relate cluster algebras and polylogarithms, you would have gotten very close to the amplitude, and the only thing that you have to input to actually get the amplitude is, as I mentioned, like smooth behavior under collinear limits and analyticity, which I didn't get into, but these are relatively easy things to just implement. So you can start with an ansatz, where you take this huge polytope and you apply this function over all the subalgebras, and then you just impose smooth behavior, just impose physical behavior, again, smooth under the collinear and analyticity, and the only thing that you can get is the amplitude. And so that's actually by far the most efficient in a purely algebraic way to calculate this amplitude, is to, given a cluster algebra, write down the kind of broad function over these subalgebras, and then you can fit the ansatz with physical limits.
So if you want to use this to write down now R28 or
Yes.
delta R28,
That's right.
you say, oh, it's going to be written as a sum over E6 subalgebras?
So no, you would still start, you would actually stay with, well, that, I would hope that there is a way to do that.
But
I
you're
haven't,
just saying,
stick
start
with A3.
A3s, but
Yeah.
you would have to look at all the different ways of putting A3s into the GR, whatever.
4,8. Yeah, exactly. Yeah, so you would look at, you would just set it as an ansatz with all the A3 subalgebras with just coefficients in front of them, and then you take the collinear limit and set that equal to the 7-particle amplitude, and that fixes essentially all of your coefficients.
And the f is it the same? No.
Yeah, it's the same. It's always the
Just
same.
one.
Yeah, there's just one function. You can look it up in the appendix of our paper. You can define it various ways. Again, the actual functional form isn't so important, as is the fact that as its coproduct. So again, yeah, I'll end here, but hopefully I've convinced you that we can get really close to n equals 4 Yang-Mills by asking questions, particularly about cluster algebras and polylogarithms, and a general, let me say, kind of takeaway idea, and this is really, again, pie in the sky idea, but one dream from this kind of methodology would say that if you want to calculate an amplitude, hopefully in realms other than n=4, 2-loop, etc., you could start with some kinematics, some kinematic space, and then again to that space you associate a cluster algebra. To that cluster algebra, you can associate, essentially a polylogarithm function, and then that just, with a little bit of extra physics, can just be your amplitude. And again, this is all purely algebra, and no integrals necessary, other than the ones in your polynomials. So anyway, that's I'll conclude. So, and I will just say, in case Dan was going to bring this up, the tricky thing about GR48 is that that's actually an infinite cluster algebra, so as you had questioned earlier. But there are ways to define finite subsets. There would be it's clear to us, I think, how to define the finite subset that would be relevant for the 2-particle 8-loop, or 2-loop 8-particle. And as you go in higher loops, the conjecture is that that size grows. So that's one final thought.
Can you see the structure from the integrand?
Right. So yeah. So the connection with NEMA. So far, it's not entirely. So far, I don't think it's entirely clear, because their mutations change around these bipartite graphs that they have, and these square moves are their mutations. So their mutations really relate like equivalent representations of the integrand, whereas our mutations are actually like generating. Like you have to do a sequence of mutations to generate the amplitude. So it's not exactly clear to me, but I think it is the opinion of people much smarter than me that there has to be a relationship. So at least Goncharov and Nima are sure that there's a relationship, but we haven't figured that out yet.
Sorry, this is a broad question.
Yeah.
Could you comment a little bit on, I mean, you mentioned sort of this hope that these tools might be applicable outside of any particular angles. Do you have any feel for sort of what subsets of things are likely to be useful and which ones it's unclear yet? How?
Just kind of more broadly, yeah.
Yeah, I mean, how strongly is n=4 playing?
Yeah. Oh, that certainly that's a great question. So it's definitely playing a very strong role in even kind of defining the kinematic space that we're looking at, yeah, I don't actually know. So let me kind of say give you an even more broad answer, which is that or a question like how special is it that cluster algebra is appearing here? Is this some deep statement about n=4 Yang-Mills and that kind of thing? And I basically heard that, at least from a lot of mathematicians, are starting to view cluster algebras as just a thing that appears in a lot of places, much like integration just appears a lot of places because it's a useful thing to do generically, and that cluster algebras fall into that case where it's just a generically useful, when you have a quiver, or you can view a quiver as being a part of your thing, then it's a useful thing to do. So for, I think, a more immediate takeaway for people in the audience is that cluster algebras are cool, and if you have quivers, you should be mutating them and see what you get. And I don't know how we can start thinking about other non-planar Yang-Mills or something like that, and start implementing cluster algebras there. But I don't think it would, maybe it would work, maybe it doesn't, but I haven't looked at it too closely yet. So, yeah. But you should download the the Java applet. It actually has like video game music. It has Mario music that plays and mutate. So yeah. Any questions?
Well, thanks.
Okay. Yeah.